Wonderful. And now we're going to move on to our last press conference session of this morning. But as a reminder, we have one again at 11 and at 2 p.m. in the same place. So our last one is about reducing underwater noise when installing subsea structures by Junfei Lee from Purdue University.
Hi everyone. Yeah, I think you can hear me. I'm an assistant professor from Purdue University. Today I'm going to talk about our design of foldable acoustic material for underwater noise mitigation method to denoise. As we know, we are currently relying on the oil and gas, right? But eventually they will deplete. And during this so we have this strong motivation to move toward clean energy in the future, right? But one of the clean energy that we are looking at is the wind energy. So on the sea, we have a high wind, right? Then we're moving this offshore wind farm to the far and far sea in the future. And we are building them bigger and bigger. But during this installation process, what we do is we install a huge pile into the seabed and use a big hydraulic hammer to hammer it into the seabed. When we are working in the room, right, when we put a nail in the wall, right, it's already pretty annoying. Now what about the nail size is like 10,000 times bigger? Right, so that is extremely annoying, especially for the sea animals like dolphins, whales, and other sea creatures, right? To give you some sense, right, these wind farms are huge, right? The blade size can be as long as 150 meters, and the surface areas go around is like 9 acres or something, or even bigger, right? In the future, when we do these constructions, right, these constructions are super noisy and super powerful. And in the future, when we're moving to a larger and larger gigawatt generators, right, we need a larger pile, right? These piles can go from 10 meters to 15 meters or even bigger, right? So you can imagine these noises can be bigger and bigger and bigger, right? And the frequency can also go lower and lower. And this is particularly annoying because low frequencies, they have a long wavelength. They propagate very far away from the pollen site, right? All these factors can have a large harm to the sea animals. For example, the behavioral changes or some auditory or physical changes of these animals. There are a lot of ways and actually a lot of regulations to reduce these noises, right? I'll give you some of these mostly used ways, right? One thing is we can use a casting, right? Stainless steel casting, but they're huge, right? We were talking about the order of like hundreds or like 500 tons of this structure, and that would put a lot of stress to our cranes and operation vessels, right? Nowadays, the best way to do it is using what we call the bubble curtains. What the bubble curtains do is we have a long pile with perforated, and then we have a service ship on the sea to pump in a large amount of air so that these tubes in the seabed can have these bubbles escaping and rise to the sea top, and then they form this bubble curtain because the air is a very good reflector for sound in water. They have a large impedance mismatch. But there are also problems. For example, they provide about a 20 dB level of noise insulation, which is pretty good because to give you some numbers, 20 dB will correspond to about 1% of energy going through this material or this bubble curtain. Right? But now if we want to further reduce the noise, right, we can think of, okay, let's use another level of the bubble curtain. That will jack up the price for sure, and also that will make the overall effect is only increased by 3 dB, not that much, right? Still something, but not that much. Okay, so there are also problems. For example, the bubbles are larger than controlled. When we release them, they're free, right? Also, that we will require a service vessel, which is a very high cost. When we talk about this cost, it's about millions per day, $millions per day. That's huge, right? Some other ways, for example, the hydro sound dampers using these resonating balloons to reflect the sound. And we also have a pretty, well, not we, but our UT Austin folks have this commercialized company with these Helmholtz resonators in the sea to use these array of resonators to reduce the noise. But when we use these resonators, right, they typically have a narrow band. They can achieve a very impressive peak noise reduction at several certain frequencies, but not a wide range, right? So if we live in the ideal world, right, what would be ideal for the noise reduction, right? We want to have a strong noise reduction. We want to have low frequencies. We want to have a cost-effective in fabrication. We want this broadband and easy to transport and store, right? Any small change that we talk about here will translate into millions of dollars per day or this kind of scale. So anything improvement will be pretty important, right? In this talk, what we'll be talking about is our effort in building these metamaterials to reduce the noise in water. And what we are envisioning is this kind of acoustic screens made of these waveguide. We design this waveguide mode carefully so that the wave propagating in them is evanescent wave, what we call evanescent wave. So instead of propagating, they decay exponentially. So we can achieve a pretty strong noise isolation. And we specifically make them like foldable so that we can, if we are not using them, we fold it and transport it. When we're at the site, we expand it so that we can deploy them and install them during the installation process. So this is our fabrication, and I'll directly jump to, without talking too much details about how they work, but I'll directly jump to the results. So in our lab experiments, we tested this metamaterial, and you can see we can increase from previous state of art of about like 20 dB average into about 40 dB average. So what that means is about like we're changing the transmission energy from like 1% to about like 0.01%. So and within a pretty large bandwidth from let's say 1.5 kilohertz to about 15 kilohertz. So we're pretty excited about this result because it's a good insulation and a very broad band. We're talking about like 2 octaves, 3 octaves on the scale. Okay. To conclude this talk, I want to say some final notes, right? High intensity impulsive noises, actually they pose a wide range threats to a wide range of sea animals, not just the whales and dolphins because they are cute, right? They can cause behavior change. They can cause physical and psychological damage to them. And also, not only these, but also sea turtles and the fishes. Also, another type of animal we largely kind of ignore is the animals that live inside the seabed, right? All of the whales and dolphins, they can escape away before we started installation, but these animals living in the seabed, they can't, right? Another thing is like a human-generated noise. They are critical, and yet pretty often like hidden because we as a human cannot hear them because the sea, when we have a large sound in the sea, right, the transmission into the air is pretty small. Right, so we don't notice them, but they are very important. So in the future, we're thinking about like not only applying this technology into the power driving process, but also like building bridges, right, the oil industry and the ship and protecting, and also like during the operation of these wind farms, because so that we can provide this continuous protection of the sea animals in the future. So that is all I want to talk about, and then I would thank the DOE for the generous support.
All right. Thank you so much. Really, really cool to see the metamaterial already in production. How long or what are your next steps to actually deploying this?
Scale up. That's for sure, right? We're going to scale in the next 2 years, so we'll be scaling up this technology to, let's say, a pound scale, and then to a brick scale, and eventually we're looking at commercializing it, and then look at the real, like, tens of like 20-meter scale of these devices.
What material? Can you talk about the fabrication process for it?
So in this lab scale fabrication, we use the 3D printing resins.
Got it.
Yeah.
All right, move to some online.
So we have one question at the moment from Anushay Bandari. Anushay asks, how long does the monopile installation take? In other words, what is the time scale at which this process is affecting marine life?
For example, like for the whole afternoon, right, for one pile. But when we install this offshore wind farm, we don't only use one, right? We put an array of these offshore wind farms in the like deep sea, so that we're talking about like couple of days.
Gotcha. And one more question from Avery Thompson. Avery asks, have you received any interest from commercial partners, and or are you working to employ this product on an active construction site?
Actually, we have an active partner for this project, so we're developing this technology together to scale it up. Yeah.
Great. That's all of the online questions. Thank you.
Yeah.
All right. Thank you so much.
Yep.